Hi, good day. So this is Chet 161 and I will be demonstrating to you a DWSIM simulation from a problem taking from Basic Principles and Calculations in Chemical Engineering 8th edition. This is your example 6.2, which is a material balance for multiple units in which no reaction occurs. So as you can see, here is the problem. Acetone is used in the manufacture of many chemicals as a solvent. In its latter role, many restrictions are placed on the release of acetone vapor to the environment. You are asked to design an acetone recovery system having the flow sheet illustrated in figure E6.2, which is here. This is our figure. All of the concentrations shown in figure E6.2 of both gases and liquids are specified in weight percent. In this special case, to make the calculations simpler, calculate stream A, F, W, B, and D in kilograms per hour. Assume that G is equals to 1400 kilograms per hour. So here we have three unit operations. We have the absorber column, distillation column, and condenser. So we will now go to our DWSIM application and simulate this example 6.2 problem. So we go over to our file and create a new process simulation model. As you can see, this is our introduction. This what pops up the moment we open the DWSIM application. I've already opened it earlier. So we click next and we now choose the compounds that we will be using for our problem. As you can see, we've got acetone, we need air, and lastly is water. So let's check three compounds. Okay, we've got air, acetone, and water. The next step is that we will be choosing the property packages and we will be choosing route slow this time. And for our system of units, as mentioned by the problem, the mass flow rate is in kilograms per hour. So we will be just setting temperature in Celsius, pressure at ADM. It's not that really significant to choose other units as well, like Kelvin or Pascal, as long as we are operating in a standard operating conditions. So we got our mass flow rate, which is our kilograms per hour. We're gonna finish. So here is our simulation. Now we will be putting our streams and unit operations in the DWSIM. So first, we will be needing absorber column. We have here columns which is absorption column. However, if we choose absorption column and we open it, it's complicated, and what is given in our problem here is very little. The details that we'll be needing in order to configure this absorption column, that's why it is not applicable to choose. We are only given a simple problem, as well we will not be needing the absorption column or absorber column. So we will be deleting this one. However, we found a way in order to represent our absorber column. We will be using two operation units that are found here in DWSIM application. And first, we need our mixer. Why is it that we are going to need the mixer? As you can see here in the flow sheet, we've got two feed streams, which is the water stream W and the entering gas stream G. So they are being mixed together, and the observer column has two output streams, which are the air A and the F stream. Our first unit operation will be needing our mixer. So we've got our inlet stream one. You can directly or automatically connect this one. By the way, first you need to pause our flowsheet calculator so that we will not be going over and over to these values. And then, of course, let's not forget our outlet stream, just only one because we will be mixing the streams into one, and then it's result in a one outlet stream. And then we will be renaming this object as W stream and the G stream. So both of these streams are the feed stream. And then the output stream, we will be naming this W plus G. So as you can see, this is not the output that we are expecting. We are expecting two output streams, which is the A and F. How do we do that? So we will be using another unit operation, which is found in separators and tanks, and that is your compound separator. So compound separator basically separates the compounds in the inlet stream. So we will be using the W plus G inlet stream and the outlet stream, and we will be automatically generating the outlet stream 1 and outlet stream 2. So let's not also forget the energy stream that is needed in the compound separator. Now, we now have two output streams, which is the A and the F. These two unit operations represent our absorber column in a way that it is simple. Because if we will be using, again, absorption column here, it is not applicable because the required information or details is not given in the problem, and we have very little details. That is why we will be using mixer plus compound separator in order for it to represent our absorber column. As you can see here in our F stream, it is separated into two streams. So distillation column, again, if we will be using distillation column, it's complicated. We will not be using our distillation column. Since the F stream is being separated into two, we will be using again our compound separator. We will be connecting the inlet stream to our F, which is one of the outlet streams from the first compound separator, and then we will be automatically generating our outlet stream 1, outlet stream 2, and of course our energy stream. Here, as you can see, for our condenser, we don't really need any unit operation for this condenser because what comes out in this distillation column is just has the same percent of the compounds that are present in it. We are done with our flow sheet, and we have represented it, or we have applied it into our DWSIM application. We will now be inputting our mass flow in the G and W. We will be tweaking first our compound amounts that are present in a particular stream. So in G, 0.03 acetone. Our air, we have 0.95, and for our water, we got 0.02. And then for our stream conditions, as given in the book, we've got 1,400 kilograms per hour of mass flow. The temperature and pressure, since it's not given here, we will be assuming that we'll be operating in a standard operating conditions, which is in 25 degrees Celsius, and the pressure is at 1 atmospheric pressure. W, as you can see, we are not given with our mass flow. Now, how do we find our W? Because we will not be generating the mass flow when we are asked of our feed. How do we do that? We will not be solely relying on the DWSIM, but we will have some manual calculations as well. In order to find our W, we will be doing mass balance. So as you can see, I already have computed the mass balance. So in air, this is 1,400. In and out in the absorber column. For our A stream, we've got 1,400 multiplied by 0.25 divided by 0.995. So the A stream, we got 1,366.68 kilograms per hour. Our F stream, we've got 221.05 kilograms per hour. Now for the mass balance of our W, we've got, substituting from the calculations, we've got our W, which is 157.88 kilograms per hour. So we will be inputting that was 157.88 kilograms per hour of our mass flow. Our G is 1,400 kilograms per hour. Let us also not forget about the compound amounts that are contained in our W or water stream. Of course, it's pure water, which is 100% as you see here in the flow sheet, putting an amount of 1 here while the other are 0 and accept changes. Now we're down to tweaking our compound separator. Here in our compound separator, as you can see, we have specifications for mass flow, molar flow, mass molar flow rate, and inlet molar flow. And for separation factors that are specified only to one outlet stream. For our first compound separator, first outlet stream A, and for our second, we have outlet stream F. The thing here for our compound separator, the value of these compounds is directed for a specific outlet stream 1, which is the A stream. We cannot directly assume that the weight percent are the values that we need to put here. So for example, if I were to put 19%, for example, versus say outlet stream 1 that contains air and water, so we'll be setting our acetone's value to 0, and then for our air and water, let's say 99.5%, and water for 0.005%, we will be having a mass flow of 1,294.1 for A and a mass flow of 263.66 kilograms per hour F stream. But those are not the values that we are looking for in A and F streams, and they rather have a huge difference. That is why we need to proceed to trial and error on this compound separator. Let us say we put not necessarily like they should be equal to 1. Let us say we need to put 100% of inlet mass flow for air and the setting for 10 for water, then we could get pretty close, 1,318. So how do we know that we got the exact value? Well, it is based on the compound amounts. We got 97.89% of the weight percent of air contained in the A stream. So if we take the maybe a water like 15, we can have an improvement of 96% stream conditions of 1,326.81. Let's say we got it for like 20, then we will now have a lesser amount of air and water, but for our A and F, for the mass flow, it's pretty close. As you can see, 1,335.55. And for our computed value is 1,366. By the way, this is not 1,366. This is 1,336.68. So that's how we got our mass flow rate. You can see here for compound amounts of F, we've got a pretty close molar fraction here. That's what is given in the book. Like 81%, 84%, they are quite close for F. And the most important thing is that we have no air here. And for air, it's not 99% exactly, but it's pretty close. And we have our string conditions, our mass flow, it's almost as exact to our calculated value. And let's check for the mass flow rate for X string. We got to 221. Yes, we have the correct answer. And we will be doing the same thing to our compound separator. As you can see, for example, if we use the distillate stream, it's D, if you're using it for outlet stream 1, for example, B, setting our air to 0, while the water is 99, the acetone is 1%. You can see that the D and B streams are incorrect. We look into our computed answer, so that's not there. So how do we solve it? Again, we will be using trial and error. It doesn't matter if it exceeds to 100%. Here we say that we got an acid 30% of acetone. We've got a, for example, outlet stream 2. We always look for the compound amounts. In water, we've got 90%. It's pretty close. And stream conditions, we're pretty close. 186, say 55, 6, 57. Yep. We got it. And then for our compound amounts, it's 94. Yeah, we've got higher amount of water. As well for our D, for our compound amounts, we assume that we had 100% of acetone for D, so it's almost exactly the same, 99.99. Okay, so that's how you do it. And then for our stream conditions, we've got, it's not exact, but we always look for trial and error. It's such a sad thing about this compound separator because we will be eventually, let's say, 35.5. Yeah, this is the value that we're looking for. And the compound amounts, 99 point something, as shown in the weight percent in the flow. And for our B, It's not exactly 96%, but very close to 90%, as long as we have our right. The thing about compound separator is we need for a trial and error in order to get the right mass flow, and because the outlet streams in each of these compound separators, we cannot edit them. We cannot decide what should be in here, what should be in the air, how many amounts of air or water, like what is shown in the problem. So it's really hard. Now, a lot of you might be asking, why not use, or if we are using our stream mixer, why not use stream splitter? So if we were going to use for stream splitter, the first problem is we cannot decide the amount of the compound on each stream. And then lastly, we ought in a split ratio aspect. If we were to like stream mass flow specs, it's in kilograms per hour, it's not in weight percent. That's why compound separator is it's an option. It's not that good because it's quite hard. Our group is really having a hard time also in simulating this problem. So stream specs and then stream split ratios, we cannot also apply that one because it's not given as ratio in the problem, but for weight percent. That's why we cannot use our splitter. So to check it off, we got our A, which is 1366. We've got the right answer for F also. For the stream conditions, our molar flow is 221, and the D and B. When you include compound separator in problems, the values here doesn't again represent the weight percent of the A stream or the output stream one. Likewise for the second compound separator. So that's it. Thank you for watching.